Okay, we'll go ahead and get started. Today's lecture is going to be on learning the reactions of aromatic compounds. So specifically what including this lecture, the last three lectures before your exam, it's really the chemistry of benzene alone. So that's the aromatic compound we're going to study. Any questions before we get started? So we're focusing on benzene really as the main scaffold of aromatic compounds and really how to transform it into other things. So there's one mechanism we'll learn. I'll take that back. Two, the primary mechanism is substitution. So as we see here to the left, there's benzene. So it's C6H6. And as we said, there's 4 degrees of unsaturation. And due to that property of aromaticity, even though we're representing those double bonds to look like alkenes, they don't undergo double addition, they just undergo substitution. So the electrophilic aromatic substitution has 2 parts to it, and we'll show that mechanism. So we're going to take benzene and learn how to make these other things. And so a monosubstituted benzene, that just means we're taking an H and we're substituting that H for some other functional group. The molecules shown here have electron donating groups on them. And this is either through induction, that's through bond, or resonance. I'll just say E density movement. So the way the slide is arranged, according to the order on the left, benzene's the benchmark. And if you substitute that H for any of those other functional groups, you see those functional groups are electron donating groups. So relative to benzene, they do subsequent reactions faster. So benzene with a methyl group is called toluene. With a hydroxyl group, it's called phenol. With a methoxy group, it's called anisole. With an amine, it's aniline. And then fluorine, it's fluorobenzene. So we'll learn how to take benzene and make not all of these compounds, but some of them. And then really the crux of the issue is once you have a monosubstituted benzene and you want to run a second reaction on it, where is the substituent going? So when you start with benzene, all these H's are equivalent. So it doesn't matter which one you substitute. But if this was your starting material and you wanted to put a second group on there, in terms of the unique positions, these two are the same, these two are the same, and that's different. So in theory, if you started with toluene and you wanted to do another substitution, you could end up with 3 different products. But as we'll see, due to either induction or resonance, that group is going to point you into which position the next reaction will occur. So the first part of the lecture is understanding the substituent effects through induction or resonance. Then we'll get into the electrophilic aromatic substitution mechanism. What are the conditions for getting those substituents on? And once they're on, how do they influence subsequent reactions? So hydroxybenzene is called phenol. And the question is stating, which of the following is not a resonance hybrid of phenol? So I'll give you a hint. A is phenol itself. So remember, resonance is the movement of electron density. It's not the movement of atoms. So which one is showing the movement of atoms? So D is showing that H on the oxygen moving to a carbon. So that's a separate sort of process that's not resonance. But as we'll see, how resonance can guide us. We know that this oxygen has 2 lone pairs. And so we can drop that lone pair into the ring. And so that's what we mean by an electron donating group. That electron pair is pushed into the ring, and the ring now is more electron rich. So those would be the resonance hybrids for phenol. So remember we said in any reaction that's not an acid-base reaction, we use the terms nucleophile. That's the thing that supplies electrons, then electrophile. For this module, in these reactions, the aromatic ring is the nucleophile. So that's supplying the electrons. When you look at these resonance forms, if we're doing a substitution of the ring, we already have a substituent. If we wanted to predict where the next substituent was going to go, the resonance forms tell us. Because if the ring is supplying the electrons, you see those electrons ending up in certain places, right? So it ends up here, there, and then back next to that OH group. So where does it not end up? So if we count 1, 2, 3, that negative charge never ends up in that 3 position. It only ends up in the 2 or the 4. So electron donating groups, when you do another substitution, will end up 1, 2 or 1, 4. And so that's how we rationally predict how we can get these substituents in with the relative locations to one another. So just as a preview question, if electron donating groups, so E, D, G, if they go 1, 2, or 1, 4, where do you think an electron withdrawing group? There's no 1, 5. Well, I mean, we call it 1, 3 because 3 and 5 are equivalent. So 1, 3. So an electron withdrawing group is going to go where the electron donating does not. And so that will also be explained through the resonance argument. So electron withdrawing groups, or EWGs, will tend to have a positive charge at the benzylic position. So To recap, when I say benzylic, so for example, in toluene, that atom, whether it's carbon, nitrogen, oxygen, or whatever, is called benzylic. So that carbon in particular is a benzylic carbon that's sp3 hybridized. So notice the way that this slide is organized. We have benzene on the right. And as you put these substituents on, they react slower than benzene in terms of the rate. So the first three to the left, they all have carbonyls. Then you have the nitrile, then CF3, and then NO2. So it says electron withdrawing groups are less reactive than benzene itself. And so the difference will be because that benzylic position either has a formal positive charge or an atom that's electron withdrawing. So this is the only one right here that's induction. Because carbon with 3 fluorines are all sigma bonds. This is an induction. The rest of them are resonance arguments. So same thing, but now with an electron withdrawing group nitrobenzene. So that's the expanded Lewis structure of the nitro group for nitrobenzene. You'll notice the nitrogen atom's plus charged. So it's electron deficient, and therefore it's going to start pulling that pi bond density out of the ring. And so the electrons from a pi bond now have to come out and form a CN double bond. So before I draw the structure, what charge is that going to place inside the ring? A positive charge. So if we look at the possible answers, A has a negative charge, so that has to be wrong. So that positive charge ends up right next door to the nitrogen. So plus so that position is plus. Remember a couple minutes ago for electron donating groups, it was minus. If the reactions we're talking about, if the benzene ring is supplying electrons, a plus charge means there's no electrons, so it can't react at that position. So we'll see that plus charge moves around the ring in the same fashion. So now you're thinking inversely, I guess, where there is not the plus charge is where a subsequent reaction will take place. And as you look through them, it's 1, 2, 3. So these 3 positions are equivalent, so either one. So the theme of this, we're taking benzene, we're going to learn how to put groups on it. So that's a monosubstituted. How does that group affect any further reactions we do? Any questions? Yeah.
I thought you said electron withdrawing groups will substitute on 1, 3.
Yeah.
So
So 1, 2, 3. It has to substitute where the plus charge is not.
Okay.
And again, that ties into the electrons in the ring acting as the nucleophile. Questions? So again, just to highlight, we're not doing electrophilic addition as in alkenes because of this stabilization from aromaticity. So we do electrophilic aromatic substitution, or EAS. And to highlight, an H on the ring is being substituted for an electrophile. The mechanism, as we'll see, regardless of what the electrophile is, the mechanism is the same regardless of the reagents. So as we'll see with the conditions, we have our electrophile, but sometimes we also have to add additives that will help us match the reactivity of the nucleophilic benzene with the electrophilic reagent. And most of the time, those additives are Lewis acids. That helps lower this gap between the nucleophilic benzene reactions and the electrophilic reagent. So the first set of conditions, what I'm going to show you, again, this is EAS. So electrophilic aromatic substitution. The first part of this lecture will focus on getting a heteroatom onto the ring. Those are a little bit more straightforward. And then towards the end of the lecture, we'll see how do we get a carbon atom onto the ring. Those are a little bit trickier because there's other things that can happen. So if we want to get a halogen such as chlorine or bromine, so F and I require other things to happen before we can do those. But chlorine and bromine, we can use the molecular halogen directly, so Cl2 or Br2, and then also a Lewis acid that helps the electrophilic properties of the X2 reagent. To get sulfur onto the ring, called sulfonylation or sulfonation, we use fuming sulfuric acid. The fuming means that there's sulfur trioxide bubbled into the sulfuric acid. And then nitration, putting a nitro group on. And that uses nitric acid and sulfuric acid. So you might have a question, why do we need to use sulfuric acid if we just saw it for sulfonation? Nitric acid isn't strong enough to form the electrophile, so we have to put sulfuric acid in there as well. And you make this brew that will then create the appropriate electrophile. So in terms of the reaction, just looking at it, as I said, it's a substitution. So you're substituting H for a halogen. In this case, we're using chlorine, Cl2 plus the Lewis acid, aluminum trichloride. So chlorine itself, it's not properly matched with benzene. So we put in the Lewis acid. And notice of that Lewis acid that it's tri-coordinate. So it does not have an octet. And maybe I can redraw this. So it's a planar compound, and the aluminum has that empty p orbital that will help engage the Cl2 to make it more electrophilic. So overall, now we're just taking benzene. It doesn't matter which H, they're all equivalent, and substituting it for whatever our electrophile is. Yeah.
So on the last slide it said or, so does that mean it's or between the aluminum or an iron or between all three? So like you have to have the Lewis acid in there?
So for example, you can use aluminum trichloride in this case, or iron trichloride.
So it can never be the chlorine alone?
Correct. So on the next slide, we'll show why you need that stuff in there, what's generating the electrophile, how does the substitution take place. So we know looking at it, one of those H's is going away, and it's being substituted for chlorine. And so where does the H end up? When we look at chlorine, we see it's diatomic. They're the same element. So there's really no charge separation between the two chlorines. You know, you might have some induced dipole, that sort of thing, but it's not really changing either atom to be more positive than the other. So the Lewis acid, because it has that p orbital, one way to think about it, that p orbital wants to be filled, so we can cleave that chlorine-chlorine bond. That's going to generate Cl plus, and then we would balance the plus with the aluminum minus. And so now this is electrophilic. So the benzene is going to supply the electrons through the pi bond. So maybe I'll put a dot. That's the carbon atom I want to use. So that's called an addition. And then the second part of it, because now we're starting aromatic, we agreed that this obeys the rules for aromaticity. We're forming this intermediate where we disrupted the aromaticity. So now it's less stable. We want to restore the aromaticity. So the carbon with the blue dot, where we substituted, we have to eliminate that H. So, I can think of that AlCl4 minus as just being Cl4 minus plus aluminum trichloride. And that's going to give me the base that can abstract that proton. So Cl minus can abstract that. and do an elimination, which restores the aromaticity on the ring. And so we remove that H. So this has a word called ipso, so ipso substitution. Yep.
Is that positive charge on that portion of the ring where it's being transferred with the other chlorine to eliminate the hydrogen? Is that positive charge on the carbon itself or on
Yeah.
the hydrogen next?
It's on the carbon. So that's pretty much the mechanism for all of these reactions. Because really what's only changing is the nature of what electrophile you're starting with. So the first step is always an addition to the ring. You get an intermediate, and then you have to do an elimination of that hydrogen. And then formally what you're ending up with is substitution. So the main thing is when you're starting with benzene, it doesn't matter which H, they're all equivalent H's, then you get your substituent on. And as we'll see, more on Monday and next Wednesday, once you have these mono-substituted ones and you want to build up like a di-substituted or tri-substituted benzene, now it's a little bit more complicated because you have to predict where the substitution is happening. So bromination, I'm not going to write the mechanism for this because it's pretty much the same. The bromine reacts with the FBr3. That forms your Br+. That's the electrophile. It does the substitution. So H is now going to Br. And you have bromobenzene. So as I said, fluorine and iodine, so like F2 or I2, are really not used in this purpose. They're introduced in another way that we'll see in 15 or 20 minutes. So mechanistically, to describe it, in the halogenation of a benzene ring, the Lewis acid, so that's of the form M is the metal, and then X is just the matching halogen of your X2, helps activate that X2 towards attack. And so the best description would be, I believe, B. So a lone pair of electrons from the molecular halogen will attack the electron deficient metal, and that generates your electrophile. And as I said, since you're learning a lot of different reactions and reagents now, when you do get to the final exam, you're going to have to know the context of those reagents. Because, say for example, Br2, Fe, Br3, Br2 light, sodium bromide. We saw in Organic 1 a reagent called NBS. Those are all bromine-containing reagents, but they only do specific reactions on certain functional groups. So in studying these problems, you have to know, okay, what functional groups do I have? What are the choices of reagents given? And how are they going to act upon those functional groups to give whatever product? So for example, like sodium bromide, the bromine is Br-. It will not participate in this mechanism. So here you have some mass spec data. And some substitution of benzene has occurred, H for X. And remembering about mass spec and isotope patterns, what reagent conditions do you think were used? So maybe a little refresher here. So on the x-axis was mass to charge, that's the Z. Z is typically 1, so you're just looking at mass. So mass is increasing that way. The highest mass you see is called the parent ion. And that's basically giving you an indication of the intact molecular formula. Any other signals that you see at lower masses were called daughter ions, and they result from fragmentation of the parent. So looking at this region here, what can you tell about the signature of those two peaks? So it's a 1-to-1 ratio. And that was which halogen? Bromine. So we can eliminate anything with chlorine. And I said sodium bromide is Br minus, so that's not electrophilic. So their choice has to be D. So that's how we get chlorine and bromine on. What about sulfur? So sulfonylation makes this functional group here called a benzene sulfonic acid. And so we all know H2SO4 is sulfuric acid. So that's the Lewis dot structure of sulfuric acid. A benzene sulfonic acid is like the organic version of that. It has some carbon stuff in it. It makes it soluble in organic solvents. The electrophile for sulfonation, is SO3, sulfur trioxide. And really all that is, it's bubbled into sulfuric acid. And so it's putting SO3H group on there, a sulfonic acid. So this H here has a pK of -1. This H here has a pKa of -9. So you can see by substituting the OH for the benzene ring, you reduce the acidity by a factor of 10 to the 8 because that was a log scale. So looking at the sulfur atom now,
So in the mechanism, what's the mechanism going to look like? What are the released as a byproduct?
so it'll be the same mechanism, but then SO3 is your electrophile. And then the sulfuric acid will protonate it to give you the H in the sulfonic acid.
Okay. And then would water like come out as a byproduct?
Yeah, you'll have water as a byproduct in there. So keep in mind, concentrated sulfuric acid, even though you're bubbling SO3 into it, I think it has a concentration of 98%. So there's 2% water. HCl is like 37%. So none of these acids that we use are like 100% that. They're typically an aqueous solution. How do you think the sulfur functional group affects the reactivity of the aromatic ring? So the benzene sulfonic acid is more equally or less reactive than benzene. If I had the eye clickers, someone would put choice D, even though there's nothing there. So think about resonance in like Lewis dot. So the sulfur atom, in a sense, is like a surrogate of carbon. So a carbon-oxygen double bond is electron withdrawing. But you have sulfur-oxygen double bonds. It's the same concept. So if I take that pi bond and do that, I can show a resonance form. That puts a plus charge on sulfur. And so now that's going to be an electron withdrawing group. And so this would be less reactive than benzene. Any questions? So put it on, take it off. This is a strategy, as we'll see, when we want to make more complex things, we'll find that we need to arrange the functional groups in a very specific pattern. And so we can use the reactivity of those functional groups to our advantage. So we can get sulfur on. If we run sort of the Le Chatelier's principle, we can then take it off. In the grand scheme of that, what we would do is take this molecule, I'll call it A. We could take A, do some set of reactions to make a new compound where that sulfur group is going to direct it to a specific spot. Then do another set and take it back off. So that's called blocking. So we take it off with basically, instead of using concentrated sulfuric acid, we would use dilute sulfuric acid and water. Yep.
So say we add an R group on the benzene sulfonic acid on the 1,3 position, right? Because that's the most likely use that.
Right.
We do this reaction, then it will just leave the benzene with the R group, right?
Yep. Now, it might be hard to visualize, but what you have to think about is if you have other substituents on there, you want to control the relationship between that R group and other stuff. So essentially what the dot, I'll put a blue dot, that sulfonic acid on the blue dot is blocking that from being substituted. So it'll become more apparent when we start looking at substitution patterns that are not as simple. So for a di-substituted benzene, you can have 1,2, 1,3, or 1,4. But now if you go up, what if you have tri-substituted? You can have 1, 2, 3, 1, 2, 4, 1, 2, 5, in these different patterns. And so that strategy of blocking is we use it for the reactivity and also to help, as a linebacker, like protect the position of the quarterback.
Sulfonation.
So that's what sulfur can be used for. Nitration is probably one of the most important. Yeah.
Sorry, can you go back to sulfonation?
So nitration is very important. It gets the N onto the ring. So we get a nitro group on there, and then we can do downstream subsequent things with that. So it is probably the most versatile in terms of a reagent that can control the reactivity of the ring. So to do substitution of H for nitro, we're using nitric acid and sulfuric acid. So the question is, why do we need sulfuric acid? So the nitro group is electron withdrawing. So that means any subsequent reaction, I'll just say step 2, would substitute there. So a little bit about the nitration mechanism. So why is there sulfuric acid? And this is weird to think about. You're using 2 acids, but one of them is going to behave as a base. And we know that the action of a base is to abstract a proton. The pK of nitric acid is negative 1.4. Sulfuric acid, negative 9 or negative 10. Which of the following is true for the reaction of nitric acid with sulfuric acid? So those two will react with one another. One will be the acid, one will be the base. So when comparing 2 pKa's, which one will win in terms of being the acid? Sulfuric acid is going to be the acid. So nitric acid has to be a base. So we can protonate that OH group. And so it'll generate that. So we have the nitric acid is now protonated. Then we have this conjugate base of sulfuric acid. So B would be our correct response here. And then we can use that information to figure out what is the electrophilic reagent under these conditions. So the electrophile is the nitronium ion, so NO2 plus. So the reason the sulfuric acid is in there, it will help decompose nitric acid into that nitronium ion. So we'll protonate And so we have to take this thing and make N NO2 plus. How might you think that happened?
Just take the water out.
So yeah, we're going to take a lone pair and eliminate water. So lose water. And then we're still balancing that charge by that conjugate base. So that's the nitronium ion. So the EAS mechanism occurs exactly the same as with chlorination. The ring pi bond will attack. You have that H and then NO2 now, and then the conjugate base will come eliminate the H from that ipso carbon. So you get the nitro group on there. It's an electron withdrawing group. It's going to force any subsequent reactions to the 3 position. Anybody need more time? Still see some writing. So nitrobenzene, the nitrogen atom is oxidized. We can see that because it's bonded to oxygen. So it has an oxidation state. Aniline, which is NH2, that's the amino group. Notice there's no oxygens, right? We can think of heteroatoms being oxidized just like we can with carbon. So the nitro group's at a higher oxidation state. The amino group is at a lower oxidation state. And we saw through that resonance argument the effect of this substituent and how it's going to direct further reactions. So we can get a nitrogen onto the ring through nitration. And because it's at a higher oxidation state, we can then manipulate it to a lower one to form an amino group, which changes the directing ability. So I showed you this with the chlorine already, but again, electrophilic aromatic substitution. The ring is the nucleophile. It's reacting with that electrophile. That's an addition. You got to pay attention to which carbon atom you're adding to, because then the one next door is the one that gets the plus charge. And that plus charge is what initiates the elimination to re-aromatize the ring. So overall, we're doing that H substituted for our electrophile. So again, the driving force for this is to re-establish aromaticity. So let me just explain this again, explain the strategy. We're getting that substituent on. How does that substituent now affect subsequent reactions? So the resonance argument tells us an electron donating group puts electron density at those positions. Relative to that functional group, if I call that functional group position 1, right next door is position 2, and that's called ortho. 1,4 is called para. So electron donating groups are called ortho-para directors. And due to the lack of an electron density, electron withdrawing groups are called 1,3 directors, and that's called the meta position. You can only use that terminology, ortho-para, or meta, if the ring has only 2 substituents. You have more than 2, that nomenclature is no longer valid. You actually have to specify the number location of the substituents. So nitration is how you get nitrogen on. We said it's an electron withdrawing group. So it directs meta. Since it's oxidized, we can reduce it. When we reduce it, it becomes the amine group. And so that's called an aniline. So this is electron donating. So now that's an ortho-para director. The conditions for doing nitro reduction, there's 3 of them. So A, B, or C. So tin dichloride and ethanol, hydrogen gas, palladium on carbon and ethanol, or iron metal, HCl, and base. So in the lab, these are all very messy reactions. They usually end up looking very crappy. Tin, like tin and titanium, anytime you use those, they form like wicked looking emulsions. It's like if you took your bathroom cup, added water and then toothpaste and mixed it up, that's how they sort of look, just very thick and murky. Iron itself is also very bad to deal with in terms of you get like sludge looking reactions. But overall, that's how you take that N group, which is oxidized, and reduce it. And so the strategy is electron withdrawing group going to electron donating group. And so you're able to now control where you can put your other substituents. So this, again, will become more apparent probably next Wednesday when I give you, a benzene ring that has, say, like 4 substituents on it, and they're in a certain arrangement relative to one another. How do you control that arrangement? So you're making that one specific compound and not some constitutional isomer. So the reduction of the nitro group, so NO2 to the amine group, is electron withdrawing to electron donating strategy. That's true. And so if we're learning one strategy, we're going to learn the other strategy as well. How can you take an electron donating group and turn it into an electron withdrawing group? So if you take benzene and you treat it under some conditions to substitute H for X, based on the IR spectrum, what is that X group?
I think it's A,
Why do you think that?
because you don't see any unique spectra other than the high, or the aromaticity and the sp2 hydrogens.
Yeah, so if it was phenol, you'd expect to see this big thing here, right? So you don't see that. What do C and D have in common? So they have the carbonyl. So in get the highlighter here. So our 17 to 1800 region in here, we don't see a carbonyl. Additionally, since we eliminated B, because there's no OH, D, it can't be D either because we don't see the OH for the acid. So it has to be A. So chlorobenzene, really by IR, it does not really have a signature that's popping out at you. The mass spec would be a better indicator of the presence of that chlorine. You probably learned in your lab for organic 1, these are like aromatic looking peaks in the IR. If you're really tuned into it, yeah, you can pick that out, but for the most part, those tend to shrink into the baseline so you don't even see them. So ultimately what you're analyzing is sort of the lack of these signatures to zero in on that. Yep.
Does the 1600, 1500 peaks correspond to the benzene ring too?
Yeah, so these would be like these really sharp ones.
Right.
Those are your CC double bonds.
Oh, you're saying those are aromatic hydrogens? Or what do you point out by being aromatic up here?
So these really sharp ones would be your CC double bonds. So remember below like 1600, we tend to ignore that because now they're getting, they're not terribly diagnostic. I think same answer choices. Oop. I drew an I instead of an H. So what pops out at you now? So it's definitely not chlorine because it's not the same spectrum. Huh? you say D? C, yeah, it's C. So we still don't have this OH here. So that's going to eliminate those two. And really what we're focused on now is this. So that's a carbonyl. And then of the available choices, it can't be the acid because there's no OH. And then the aldehyde has that extra CSP2H stretch that pairs up with the carbonyl stretch. So again, as you think about the module exams, the final exams, you're not only looking for like what's there to confirm, but you can eliminate things by what's not there. I guess in the last 13 minutes here, we're going to we took benzene, we made nitrobenzene. That got the nitrogen atom on the ring. We can reduce it to the amine. Now we're going to look at the chemistry of that amino group to get other heteroatoms onto the ring. Because I said F, I, we haven't got oxygen on the ring yet. So how do we get these other heteroatoms on there? And they all start from aniline. So benzene to nitrobenzene to aniline. Now we can take that functional group the NH2 and substitute it for other heteroatoms through a process called diazotization. And it's we call it a one pot or one reaction process. But it has two distinct steps to it. The first step is making this thing here, which is called an aryl diazonium salt. The conditions to do that include sodium nitrite. So remember from Gen Chem how vocabulary can tell you about the oxidation state of things. So nitrate is NO3, nitrite is NO2. So sodium nitrite plus HCl and water, that generates nitrous acid. So HNO2. The HNO2 then reacts with the amine group. And notice the structure of that diazonium. It's now N2+. So somehow that nitrous acid is transforming the amine into N2+. And N2+ really is a nitrogen gas with an aromatic ring on it. So it's pretty reactive. And what it's going to allow you to do is then substitute the N2 for your other heteroatom. So this is the Sandemeyer reaction. So the amine to the diazonium to other heteroatoms like F, I, or oxygen. So it says a mechanism of nitrous acid formation and then decomposition to nitroso ion. There's going to be a lot of arrow pushing in these next two slides. So overall, what we have to do, we have to get that second nitrogen onto the amine, and then we got to get rid of those H's bonded to the amino group. So sodium nitrite is a solid. HCl is a clear, colorless liquid, is an aqueous solution. You react them together to form nitrous acid because you can't buy it. You just make it and then use it immediately. So there's sodium nitrite. We're going to react that with an excess of HCl. So this oxygen will get protonated. And then this is nitrous acid. This thing will decompose to the nitroso ion. Before I start drawing, what do you think is going to happen? Remember, you're still in the presence of a lot of HCl. Yeah, so the OH is going to get protonated, and then you're going to do an elimination. So this now gets protonated. Now you have a good leaving group, which is water, and so it will do an elimination starting from that doubly bonded oxygen. And so that's the nitroso ion. So that's the thing that reacts with the amine of the aniline and eventually will transform it into the N2 plus group. So it took me 27 years to draw that. But when you run this, it happens like as soon as you get all the stuff in there, it's boom, it's done. I mean, it happens so fast. If you let the temperature warm up too much, the reactions can actually like volcano out and make a mess. I know because I've done it. It makes a serious mess because it's spitting out N2 gas and forming that diazonium. I'm looking at the clock, debating about what I want to do, because this mechanism is really long. So I don't want to rush it. Plus we have a lot of other reactions downstream after you form the diazonium. So I think what we'll do is we'll stop here for today. Then we're going to pick up on this mechanism, learn its substitutions, and then we'll follow up with how do we get carbon on the ring. Yeah.